Once again, here we are at the physics video lecture. This is psci 168, video lecture 3. So we're in the middle of learning mathematics and geometry. The best thing for you guys to do when you take your notes is leave a lot of space, because I'm going to supply some logic for this, and just treat it as practice. So everything I do, if you do it once or twice or 3 times, it will become easier for you. Today I have a couple of very interesting applications of some of these geometrical concepts. So let's just call this geometry applications. And what you'll see is we're building everything up from scratch. So we've already made it into geometry, and the application I'm going to talk about is how we can measure the height of a tall tree. Okay. Measure the height of a tree without climbing it. A tree. So I'm going to start with my tree over here. Let's see if I get something that works. Got a tree over here, and I want to know how tall it is. Actually, when we're meeting here in place, the students go out and measure some of the big trees on campus. So yeah, I want to know how tall this tree is. And then what I do is realize that it casts a shadow. So the sun's going to come in here, and the shadow of the tree is going to appear on the ground down here. See if I can make that line a little straighter all the way down. Okay, there we go. And here's the ground. Okay, so how does that help me? I have a couple of options. Notice there's a triangle there. One thing I could do, it's kind of a historical example, I could stand here and have my shadow meet at the same place that the tree shadow meets. Okay. So now we have a geometrical construction. I'm going to go ahead and let's just go ahead and label this. So we have sun rays coming in this way, and down here we have the shadows. And you can actually see there are 2 triangles right here. This, of course, is the tree. How high is the tree? So let's go ahead and just turn that into a pure geometry problem. What we're using is what's called similar triangles. I'm just going to reproduce what I have up there, maybe a little bit smaller. So, okay, these are 2 triangles, the outside one and the inside one right here. Let's just go ahead and call the height of the tree capital H, and the length of its shadow here on the ground capital L. Then I can call my height lowercase h and the length of my shadow lowercase l. These are both right triangles, and we could use our various theorems concerning these, but the similar triangles have the same ratio of this, and I'll even note, right, same triangle, same opening angle alpha. Okay, so we have these same ratios, namely the ratio h to l, h divided by l, this h, this l right here, is, because it's a similar triangle, equal to this ratio capital H divided by capital L. Okay. It would be true for any intervening triangle that we make as well. So this is an equation, and we wanted to find out what the height of the tree is. So we write down this ratio, and the second thing is, so these ratios, they're equal, we've got an equal sign here, and then we go ahead and solve for capital H. Solve for H. And you can see how many steps it takes you to do. If you just multiply both sides by capital L will cancel on the right, and you'll be left with the answer on the left here. I'm even going to do it for you. First of all, we'll write it in this order. Then we'll multiply both sides by capital L, which cancels on this side, and therefore we have our answer. The height of the tree is equal to H times capital L divided by lowercase l. Okay, I'll put a box around that. This is the kind of thing we want to practice so we can do it with ease. Okay. So once again, these ratios, lowercase and uppercase as labeled on the sketch, and now I just solve for H, which is what I wanted to know. That's the height of the tree. And you can do this in different ways. Okay, you don't even have to have the shadow being cast. You can stand somewhere and sight along a straight line. You could aim this ruler at the top of the tree. You could measure angles. What I'm really showing you is practical trigonometry. We just want to be aware of it at this level of similar triangles. Okay. So if I were to do a homework problem, and for this, just leave the room in your notes. Leave some room in your notes so you can figure it out. I could just give something like this with some unknowns that you then have to use your knowledge of triangles to figure out. Okay. But yeah, suppose we want the height of that tree as up there, and we pace off this L, so we know this distance here. So that would be this L right here. And then this ratio, lowercase h divided by lowercase l, could actually also be the tangent of alpha, if you know some trigonometry. So homework. Suppose L equals, let's just say 30 meters, and alpha is equal to, let's say, 50 degrees. Okay. So even if you haven't had trigonometry, I'm going to show you exactly what to do. So alpha is 50 degrees. You know, you could sight up there. You have a protractor. You know what 50 degrees is. So alpha is 50 degrees. Tangent of alpha is equal to, and that's the definition in a triangle like this. Make sure we see this as alpha. Tangent of alpha is h divided by l. So if you have a calculator that'll find you the tangent of alpha in degrees, find h. Okay. So leave some room in your notes. That will actually be enough. If you leave some room in your notes, you can figure it out. It's only a couple lines. And if you're interested in the answer and you're not able to get it, just send me an email, let me know, and specify what problem it is, and I can do it on the board next time. But yeah, this is basically surveying Let me give one more example of what surveyors do, not what we do in this class. But you can see a little geometry allows us to measure the earth. And in fact, that's the meaning of the word geometry, is the measurement of the earth. So let me give a surveying type of example. And I'll just leave it there. So here's another example. Of surveying. You've maybe seen the surveyors out sometimes. Now we're looking at a top view of what they're doing. Top view. What they do is they set some baseline. They very carefully measure this line here. Say it's L, and here's some distant object. I'm going to draw the lines to it first. So here's some distant object. Okay, those lines are straight. I didn't use a ruler. They're supposed to be straight. What they will do is very carefully measure these angles alpha and beta. So if they know L very well. They've got a steel tape. They know this length perfectly. Then just by sighting on this object and knowing these angles, they can locate it exactly. Okay. And this could be the height of a mountain. This could be something, the angles could be also up, have some elevation to them as well. So L is known, alpha, beta, very carefully measured. And then this location, point P, can be located exactly. Okay, so that's what the surveyors do, and you recognize they're not quite using these similar triangles, but they're just using some trigonometry as well. You could, in fact, build this up out of similar triangles if you have a little patience. Good. Actually, similar triangles wouldn't be the method here, but you could build it up out of triangles. Now, my next example is going to be referring to this globe here. Namely, we want to measure the shape and the size of Earth. Okay. You can look this up in the book, and you can look it up anywhere, and you'll be told that the Earth is spherical, and you can look up the size of it, but I want to discuss how that was discovered, and we're going to rediscover it together. Okay. And the actual size of it will be important for other things we do later this semester. At the moment, it's an interesting historical, geometrical argument. So let me consult the clock here. Good. So our next topic is shape and size of Earth. Shape and size of Earth. This knowledge is a couple thousand years old, so it's about time we figured it out too. So first of all, we have to know both. Okay? For example, if we want to know the radius of Earth, we first have to know it's a sphere. If we know the radius of Earth, we'll know the size. But therefore, we have to know what the shape is. And there are a number of arguments that were historically made. Question mark. But actually, to know that it even has a shape, we have to think of it as a heavenly body. So we actually have to prove that Earth is a a celestial object the way other objects are. In other words, we have to be able to compare it to the sun and the moon. And in that sense, we say, well, maybe the sun and the moon are spheres, so maybe the earth is also a sphere. But the way that we know it's a heavenly body really comes from a long series of observations of phases of the moon and eclipses of the sun and the moon. So I'll put Earth as a heavenly body, that'll be question mark, and then phases of the moon are one set of reasons, and the eclipses of the sun and the moon are another set of reasons. And I'll just draw a picture that kind of summarizes the scenario and how it was discovered. So what we're going to do is have a large circle. Okay. We have a large circle that represents the orbit of the moon. We're going to put a smaller circle, that's our Earth, right here in the center. And we're going to imagine that the sun is at a great distance. So that's sunlight's coming in from a great distance here, parallel in essence. Here's the thing. Which side of the moon is the Earth is illuminated, and which side is in the dark? Okay. That side's in the shade, that side's illuminated. Now suppose we see a moon directly overhead. Okay. Same argument. Okay. Now, suppose the Earth is rotating counterclockwise. Okay. Earth is rotating counterclockwise. We're looking down, say, on the North Pole. And in fact, I'm going to draw a little stick figure here. That's pretty small. Okay, there's a little stick figure. And then you say, what time is it? Well, if we're being carried counterclockwise into the dark, that means it's sunset. So it's sunset, and I'm looking straight up and seeing a moon, and I'm seeing a half moon. Okay. If it's sunset and the moon is over here, again, I've got the light and the shaded side. If it's sunset and the moon is on the horizon, okay, I'm looking that way on the horizon, then I'm seeing a full moon. Okay. If it's sunset and the moon is up here, I'm really just seeing this little sliver of moon. Because my eyesight is from here, I'm really just seeing a little sliver. And you guys have observed all these things before. So it's these ideas, you know, the phases of the moon, we definitely see the sphericity of it. It's different, has different illumination. Now, if a moon is right here, then the shadow cast by the Earth is cast over the moon, and then the moon is actually in the dark. If the moon were right here at sunset, it will cast a shadow on the Earth. And in fact, because the sun isn't at an infinite distance, it casts a shadow that's kind of a point. Okay, but this would be an eclipse of the sun. And this over here would be an eclipse of the moon. Okay, eclipse of the sun, eclipse of the moon. And now we know the Earth really is a heavenly body. It's casting a big shadow. The moon and the sun, look, you know, are spheres. And we still don't know that the Earth is a sphere, but we do know that it's a heavenly body. What closer observation shows is that the shadow cast by the Earth on the moon is arc-shaped. So this is an important observation. Shadow that Earth casts on the moon arc-shaped. Arc-shaped. I gotta write that correctly. Arc-shaped. That's an argument for the sphericity of Earth. Also, when you're at the coast and a ship disappears over the horizon, those are also arguments for the curvature of Earth. So yeah, this whole body of observations tells us that the Earth, first of all, is a heavenly body, and second of all, it is a sphere. So only a sphere always casts an arc shape. Sphere. So the Earth is a sphere, and now that we know the Earth's a sphere, we can go ahead and ask how large is that sphere? Okay. What's its radius? What's its diameter? Good. So this was a face of the moon diagram. Got our eclipses of the sun and the moon. So when the moon casts a shadow on Earth and we're in that shadow, it gets dark. So that's an eclipse of the sun. And when the Earth casts a shadow on the moon and the moon is darkened, I've seen a couple of these. It doesn't get totally darkened, it gets much dimmer. Then that's an eclipse of the moon. Okay, so make sure you have both of those facts down. And now we'll talk about the size of the Earth. Once we know it's a sphere, there's a very interesting measurement. Okay. So yeah, I brought my globe to class. This represents the Earth, and the question is, how many of these? How many meters? How many meters would make up, say, the radius of the Earth? This is the size of the Earth problem. And I'm going to do the geometrical construction over here and then the explanation on the left side of the board. I'll just start with the name. You guys can look this up, Eratosthenes. Maybe you'll read more about that. So this is Alexandria 200 or 300 years BC. Okay, Alexandria. At Alexandria. So he reads in a book somewhere that there's a place south of Alexandria where the sun stands directly overhead on June 20th and shines straight down into the bottom of a well. Okay. So sun illuminates the bottom of a well. Illuminates the bottom of a vertical well. We're going to assume it's vertical. Bottom of a well on June 20th at noon at a place called Aswan. So I'm going to have you guys look this stuff up and print out some maps. So you've got Aswan, you've got Alexandria, and you can look these up on a map and print out some maps. So we'll have so you'll know where this is. This is on the Mediterranean at the outlet of the Nile River, and Aswan is south of that, upstream on the Nile. Okay, so here's the construction that Eratosthenes made. So on our big circle, we're going to draw a straight line out. This represents the rays of the sun. And remember, if you're on a spherical Earth, the direction up is always away from the center of the Earth. Okay? So if you're on the north, we're going to say North Pole right here. This is up, right? If you're down here, that's up, okay? That's the first thing to note. So this is the sun ray that illuminates the bottom of the well at Aswan. Aswan, okay? Now, what Eratosthenes does is he's up here at Alexandria. I'll just write Alex. He's here at Alexandria, and he measures the angle that the sun rays make. So that's sun rays, and we're assuming they're parallel, which is an approximation, but for the geometry we're going to assume they're parallel. Okay, so this is the direction. This is you have to think about this for a moment. This line here is straight up and down. This is towards the sun. So imagine here, be the same thing here in Fresno. If the sun were coming from there at noon, okay, there's the sun along the ruler, and straight up and down is my arm here, okay? This is straight up and down, there's the sun, and you can see that forms an angle. So the same thing here. Straight up and down, sun forms an angle theta, and by geometry, that's that same angle there, because these are two parallel lines, okay? Same angle theta. And this here is the north-south distance arc we're going to call S. So Eratosthenes measures, I'll just write these data down. He measures, so from my picture here, theta equals 7.15 degrees. And S is 800 kilometers. They must have used a different measurement back then. You can look that up, but we're going to say 800 kilometers, which is equal 8 times 10 to the 5 meters if you want to put it in scientific notation. Okay. Well, and I'll label the radius of Earth as here and here, and we're ready to discover the size of the Earth. So I'll do this, and you guys leave room in your notes so you can repeat the calculation. This is the kind of problem I like to have you guys discuss on an exam, where you just write it out, and I can give you different angle, different numbers, and you have to figure it out again. Okay. So you see, though, that's a geometry problem. I'm just going to rewrite it just with the symbols. And since the numbers are already there, this is actually not the similar triangles, but it's a related type of calculation. So from our diagram, from the diagram, Eratosthenes argues like this. He says, this angle is the same proportion, or it's the one in the middle here. This is the same fraction of 360 degrees as this S arc length is a fraction of the entire circumference. So from the diagram, the ratio theta over 360 degrees is equal to the ratio arc length S over 2 pi radius, because that's the circumference, right? 2 pi r is the circumference. So where's our unknown? Solve for r. And again, depending on how much practice you've had doing this, it'll take shorter or longer. Well, one thing we can do is just invert it. So we can say we've got 2 pi r divided by s is equal to 360 degrees divided by theta. We just inverted both sides. 2 pi r over s, 360 over theta. And then we can cross multiply both sides by s, cancels the s, and divide both sides by 2 pi, cancels the 2 pi. So we get r is equal to, so we've got s, we've got 360 degrees. And now I'm going to go ahead, okay, I'll put the theta in first, one more step. So s, cross multiply, and then divide by 2 pi, 1 over 2 pi. So that's the radius of Earth. If we plug these in, we have r is equal to 1 over 2 pi, and then the s is going to be the 8 times 10 to the 5 meters. That's my s. And then I have the 360 degrees divided by 7.15 degrees. I think I have those numbers right. What we're going to find, and you guys control this with a calculator and make sure you get something at least close, what we're going to get is r is equal to 6.37. This is the number we're going to use, times 10 to the 6 meters. That's the radius of Earth. Radius of Earth. Okay. So there you have it. We haven't left out a single step. How we discover the radius of Earth. You guys go ahead and calculate this. You'll notice if it had been a different city with a different arc length, if it had been theta further north, it would have been a longer arc length, but that same number would have come out each time. Okay? And it's also possible, instead of using one where the sun is directly overhead, you could do, say, what's north and south? You could do Fresno, or south of Fresno. Say you could do San Diego and Fresno. Okay, San Diego and Fresno are approximately north-south by some couple hundred miles. The angular measurements, you'd have to be very, very careful, but you could do the same calculation between those two cities. Okay. That'd be a more advanced version. This is the actual historical version that was done. So for your homework, actually, consult the clock one more time. Perfect. I'm going to leave you with some homework this time that you definitely want to include in your notes. So I'll send this up. Okay. By the way, this type of sketch should be pretty large in your notes, a third of a page, half of a page, so you really helps you understand them if you make good sketches. So here's what we want for your notebook. First of all, maybe look up Eratosthenes. If you find something good, you can print it out and include it in your notes. The next thing is we need maps. So print out maps. And like I said, this Alexandria, with Alexandria and Aswan, maybe you could have a map that shows a fairly large portion of Egypt, okay, and the Mediterranean Sea, so that you want to locate it. Now I've got the globe here. You want to locate it one time. Well, you're not going to see what I'm seeing here, but the Mediterranean is right here. So maybe Mediterranean region, and then another one that's closer up, Mediterranean region, and then one that's close up enough where you can actually get the north-south distance. So closer. Okay, so you want some maps printed out. for this topic here. And you know, if you look up Eratosthenes, you may get a nice image of what he did, and a couple of nice maps so that it looks good. And anyone who looks at your notes, including yourself, would know where this happened. You know, you'd recognize the geography. And basically the Nile flows from south to north. These are both along the Nile River. And this is, like I said, you'll get the dates on this as well. A couple hundred years BC. So, dates, you can include those in your notes as well. So that's a nice project. That'll look good. And of course, this calculation, I'll just write here the calculation, exclamation points. So what I did here, make sure you understand it, and make sure that if you plug these numbers in the calculator, something close to that comes out, okay? Then you'll be in good shape. So what I'm going to do next time, I'll just briefly discuss some other astronomical discoveries and facts. Now that we've seen how the size of Earth is measured, then we can talk briefly about the moon, the sun, various astronomical sizes and scales that may be useful later on in the semester. So I'll give you a little table of those, and then we'll move on into a little bit more astronomy, and then we'll get into forces and structures. So yeah, we're just building everything systematically. What we're going to see is we needed geometry to do some astronomy, and we're going to need these facts later. We also need the geometry to talk about forces and structures, and we're going to need forces and structures to talk about energy. So we're just building our way up to a complete discussion here. Good. Enjoy looking these things up, and see you guys next time.